Hello, welcome to Lesson 2.1, Unlocking the Structure of the Atom. So far in the readings, we've already discovered that matter is made of particles. We call these particles atoms. And atoms of the same element are identical to each other in some way. Different elements have different atoms. And we learned that these atoms join together to make compounds which make up the known universe. These atoms cannot be created or destroyed. They're only rearranged in a reaction. So the carbon atoms in your body have been around for a long time, for example. So let's go ahead and see if we still believe all those points of Dalton's atomic theory. Let's skip ahead to the late 1800s. Joseph John, or J.J. Thomson, as he used to know, was working in England with his cathode ray tubes. And his cathode ray tubes were curious little critters. Let me pull one up for you to see. Okay, here's a close-up of a cathode ray tube. Over here you have a metal plate called the cathode. On the other side you have a metal plate called the anode. They're both hooked up to some high voltage electricity. Inside there is a near vacuum, a small amount of gas, and if you notice there is what appears to be a beam of light here. They called this thing the cathode ray because it always came from the cathode and traveled towards the anode. So it looks like a beam of light. However, it doesn't behave like a beam of light because if you place a magnet near it, it will either bend towards the magnet, or if you flip the magnet, it will bend away from the magnet. And I don't know about you, but I've never seen a flashlight beam or headlight beam do that. And so it turns out that this is not, the cathode ray is not a ray of light at all, but it's a ray of particles. And because it interacts with a magnet like that, that means it has to be a charged particle. So that was the first observation and first conclusion that J.J. Thomson made then. So the first observation that J.J. Thomson made was that the beam of light is actually bent by magnetic fields, and from that he concluded it was not a beam of light at all. It was actually a beam of particles instead, and these particles had to have a charge. We now know and love these particles as electrons. Secondly, because these electrons started at the negatively charged cathode and moved toward the positively charged anode, he concluded that the electrons also had to be negatively charged. Because, as you know, opposite charges attract each other, like charges repel, so if they moved away from the negative plate, they had to be negatively charged. And then lastly, no matter what metal he used, he found that all metals formed these cathode rays, so therefore all metals and all elements had these electrons. And so then, one of Dalton's most important points of his atomic theory was disproven. Atoms are not the smallest particle of matter at all because they actually have something smaller inside of them. That something would be the electron. So Thomson knew that the atom was neutral overall. It had no charge, and so if it had negative electrons, it had to have something positive inside there too. And so Thomson just assumed the positive charges spread out throughout the whole atom in this cloud, like this jelly type thing, and then the negatively charged electrons were embedded in that positive cloud. To us it kind of looks like maybe raisin bread or a chocolate chip cookie, but apparently raisin bread wasn't real popular back in his day, but plum pudding was. And so this is known as the plum pudding model because it looks like the atom's a big chunk of bread, and then the negative electrons would be the raisins embedded in there. So how big is an electron? Well, that fell to Robert Millikan, an American, to figure that out. He used a rather ingenious contraption here. He sprayed some very fine oil drops into this contraption, and this contraption also had two metal plates. The bottom one was negatively charged, top one was positively charged. As oil drops fell through, they were ionized, which means they were given a charge, in this case a negative charge. So as the negatively charged electrons fell downward by the force of gravity, he adjusted the electricity on the plate so that the negatively charged plate would repel the negatively charged oil drop, and the oil drop would actually hover there in the air. By knowing how much charge it took to make each oil drop hover, he was able to figure out the size of the charge and then the mass of the electron. His answer was pretty darn small. 9.11 times 10 to the negative 31st kilograms for the mass of the electron. Wowzers, that's tiny. And so Mr. Thomson proved that the atom was not the smallest part of matter. The electron so far was. Was there anything else? Well, we'll figure that out. Part 2, radiation. In a few years after J.J. Thomson discovered the electron, across the English Channel, Henri Becquerel in France discovered something also pretty remarkable: radioactivity. You can kind of describe radiation as the leprosy of the atomic world. basically a large atom that's unstable will lose bits and pieces of itself over time, much like you might lose a nose or a finger or an arm if you had leprosy, and eventually you're left with something smaller and more stable. There are three types of radiation that are known: alpha particle, beta particle, and gamma ray. The alpha particle consists of two neutrons. If you're keeping score at home, you might recognize something like this as the nucleus of and 0 represents a neutron. It's actually an alpha particle has no electrons associated with it. That's why it's just a nucleus. So as such, it has a charge of +2, and it's relatively large as well. A beta particle is the second type of radiation, and this is small and negative. Basically, it's a free-range electron. It's an electron that's not bound to an atom. It's just roaming around out there in space. Eventually, it'll be picked up by an atom, and then it'll disappear. And so a beta particle is the opposite of an alpha particle. It's small and negative, whereas an alpha particle is larger and positive. Lastly is a gamma ray. Gamma ray, if you notice, this doesn't have the word particle in it. It's a ray. It's very, very high energy light. It has no mass. It has no charge. It's just light, a very, very high energy. If you're a fan of the Marvel Universe, you know that a lot of gamma rays turn the Incredible Hulk into the Incredible Hulk, or rather they turn Bruce Banner into the Incredible Hulk. In real life, if you get shot with the gamma ray burst, you don't turn green and strong and mean, you just turn dead instead. Radiation, of course, is bad for people. The worst kind is gamma rays. Alpha particles aren't as bad for you, and neither are beta particles, but gamma rays are pretty nasty for you. What happens is that when they hit the molecules in your body, they have so much energy they just rip the molecules apart. If it's a common molecule like, say, water or sugar or a protein, it doesn't really affect your body much. You're fine. The problem is, though, when it hits something a little more important, like a DNA molecule. If it ruptures a DNA molecule and distorts it, then when your cell replicates, that distorted DNA will create more distorted DNA, and it will keep replicating itself, and eventually you'll form a tumor then. And tumors don't work right because they don't have the right DNA, and so that's bad for you. And so, anyways, what this meant then was that there were other things smaller than an atom out there. And so again, Dalton's simple model of the indivisible atom was wrong. Up next then was a nucleus. Ernest Rutherford came from New Zealand to England. He won second place in a contest to study at Oxford, so he was going to end up staying at home in New Zealand because he didn't win. However, the first place guy had to drop out, so Rutherford went instead, and things turned out all right for him. What he wanted to do was he wanted to test the plum pudding model of the atom. And so about 20 years after J.J. Thomson discovered the electron and proposed this plum pudding model, Rutherford decided to test it using the famous gold foil experiment. The way this was going to work is he had a source of alpha particles right here that would be released through this small hole here, and they would strike a sheet of gold foil. The reason Rutherford chose gold foil was because gold is very malleable. You can beat it into very, very thin sheets. And so what he expected to happen were these alpha particles, which, if you recall, are relatively large and positive. He expected them to crash right through the gold foil and then hit the detector behind it. So he expected to detect a lot of alpha particles directly behind the gold foil and basically none anywhere else. His results, though, were kind of surprising. So he literally thought that the alpha particles would crash through with the atoms like a cannonball through gauze, is what he said. And gauze, if you know much about healthcare, gauze is like bandage, band-aid, and so on. So if you shoot a cannonball through a band-aid, it's going to crash right through. So this is what he expected to happen. All the particles would just go straight through the wimpy plum pudding atom as if it wasn't even there, and then hit the detector straight ahead. The actual results, though, were a bit different. Most of the alpha particles did do what he expected. They passed straight through the gold foil with very little deflection. And so from that, he actually concluded that the atom was mainly empty space. The alpha particles went through as if nothing was there because nothing was there. So most of the atom was empty space. The second observation was that a small number of the alpha particles were deflected and bounced backwards off the gold foil. And the only thing, as you know from physics, in order to change the motion of an object, even a small one like the alpha particle, is you have to exert a force on it. And there are a couple of ways to exert that force. If you have the positive alpha particle coming in here, going towards something, and it was repelled away from that something, that means that it had to hit something very massive and solid, and also something positive in order to repel the positive charge of the alpha particle. And so what Rutherford assumed then was that most of the atom was empty space. You had your electrons way out there, and then in the center you had this dense, massive, positively charged nucleus. So a surprise may have been kind of like this. Okay, so this is a clip from The Amazing Race. So they are trying to shoot alpha particles or watermelons forwards. However, things don't work out quite like they think they would. Ouch. That's gotta hurt. So anyway, he wasn't expecting things to bounce backwards at him, but they did. And so the nuclear model of the atom was born. Again, there was a dense, positively charged nucleus inside, negative electrons orbiting about, and then everything else was just simply empty space. This is also sometimes known as the solar system model because it looks like the solar system with the sun as the nucleus and the planets as the electrons orbiting around there. And then lastly, to put the finishing touches on the atoms, Henry Moseley used X-rays to determine the atomic number of the element. Later, this atomic number was realized to be its protons. Henry Moseley had a tragic story. He was one of Britain's youngest and most promising scientists. Then World War I broke out. He signed up to join, or was drafted, and he went to serve and died at the Battle of Gallipoli. And after that, Britain said, whoa, let's not send our scientists to battle anymore. So if you're a scientist in Britain, you're exempt from frontline combat. And lastly then, to complete the discovery of the atom, in 1932, James Chadwick discovered the neutron. If you notice, that's 40 years after J.J. Thomson first discovered the electron, and a good 30 years after Rutherford discovered the positive nucleus. So what took it so long to discover the neutron? Well, unlike the other two particles, neutrons obviously don't have a charge. They don't interact with magnets. They don't interact with other chargers. They just kind of sit there. And so it took a lot longer to find neutrons, but by golly, eventually we did. And so now then, to complete the model of the atom, our nucleus has positive and neutral particles inside the nucleus, and then negative electrons orbiting around on the outside. Just for fun here, if you go to the University of Illinois Chemistry Library on campus, they have a timeline of all their professors and who their professors were and who their professors were, and so on and so forth. So it's kind of a family tree of sorts of chemistry professors. I draw your attention down here to the bottom. You can barely see him, but E. Oldfield stands for Eric Oldfield. Eric Oldfield was my physical chemistry professor when I was a junior. His professor was D.E. Chapman from Liverpool. Mr. Oldfield was a great guy. English accent, clearly from England. He was good. Chapman's professor was Craggs from London. Craggs' professor was Ellis. Ellis, if you notice, had two professors. One was Chadwick, and one was Rutherford. So, boom, right there. And Rutherford's professor was J.J. Thomson. And so if you follow down the family tree, I would be at the bottom. You would be my chemistry children, so to speak. And your grandparent was Oldfield. great-grandparent, great-great-grandparent, great-great-great-grandparent, great-great-great-great-grandparent, and then that makes J.J. Thomson basically your great-great-great-great-great grand chemistry teacher. So, congratulations. Carry on the tradition.